The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we're going to do an exciting topic, which is hashing. Do it all in one lecture. That's the plan. See if we make it. You've probably heard about hashing. It's probably the most common data structure in computer science. It's covered in pretty much every algorithms class. But there's a lot to say about it, and I want to quickly review things you might know and then quickly get to things you shouldn't know. And we're going to talk on the one hand about different kinds of hash functions, fancy stuff like k-wise independence, and a new technique that's been analyzed a lot lately, simple tabulation hashing, just in the last year. And then we'll look at different ways to use those hash functions to actually build data structures. Chaining is the obvious one. Perfect hashing you may have seen. Linear probing is another obvious one, but has only been analyzed recently. And cuckoo hashing is a new one that has its own fun features. So that's where we're going to go today. Remember, basic idea of hashing is you want to reduce a giant universe to a reasonably small table. So I'm going to call our hash function h. I'm going to call the universe integers 0 up to u minus 1. So this is the universe, and I'm going to denote the universe by a capital U. And we have a table that we'd like to store. I'm not going to draw it yet because that's the second half of the lecture. What is the table actually? But we'll just think of it as indices 0 through m minus 1. So this is the table size. And probably we want m to be about n. N is the number of keys we're actually storing in the table, but that's not necessarily seen at this level. So that's a hash function. M is going to be much smaller than u. We're just hashing integers here, so if you don't have integers, you map your whatever space of things you have to integers. That's pretty much always possible. Now, best case scenario would be to use a totally random hash function. What does totally random mean? The probability, if you choose your hash function, that any key x maps to any particular slot, these table things are called slots, is 1 over m. And this is independent for all x. So this would be ideal. You choose each h of x for every possible key randomly, independently. Then that gives you perfect hashing. Not perfect in this sense, sorry. Gives you ideal hashing. Perfect means no collisions. This actually might have collisions, right? There's some chance that the two keys hash to the same value. We call this totally random. This is sort of the ideal thing that we're trying to approximate with reasonable hash functions. Why is this bad? Because it's big. The number of bits of information you'd need to, if you actually could flip all these coins, you need to write down, I guess, u times log m bits of information. Okay, which is generally way too big. We can't afford u. The whole point is we want to store n items much smaller than u. But surprisingly, this concept will still be useful, so we'll get there. Another system you've probably seen is universal hashing. This is a constraint on hash functions. So this would be, ideally you choose h uniformly at random from all hash functions. That would give you this probability. But we're going to make a smaller set of hash functions whose size is much smaller, and so you can encode the hash function in many fewer bits. And the property we want from that hash family is that if you look at the probability that two keys collide, you get roughly what you expect from totally random, which is you would hope for 1 over m. Once you pick one key, the probability the other key would hit it would be 1 over m. But we'll allow a constant factor and also allow it to be smaller. It gives us some slop. You don't have to do this. If you don't do this, it's called strongly universal. But that's universal. And universal is enough for a lot of things that you've probably seen, but not enough for other things. So here are some examples of hash functions that are universal, which again you may have seen. You can take a random integer a, multiply it by x, integer multiplication. You could also do this as a vector-wise dot product, but here I'm doing it as multiplication modulo a prime. Prime has to be bigger than u. Maybe bigger or equal is fine. Universe. And then you take the whole thing modulo m. Now this is universal, but it loses a factor of 2 here, I believe, in general, because you take things modulo prime, and then you take things modulo whatever your table size is. If you set your table size to p, that's great. I think you get a factor of 1. If you don't, you're essentially losing possibly half the slots, depending on how m and p relate to each other. So it's okay, but not great. It's also considered expensive because you have to do all this division, which people don't like to do. So there's a fancier method, which is, I guess, a times x shifted right by log u minus log m. This is when m and u are powers of 2. Which is a case we kind of care about. Usually your universe is of size 2 to the word size of your machine, 2 to the 32, 2 to the 64, however big your integers are. So it's usually a power of 2, and it's fine to make your table a power of 2. We're probably going to use table doubling. So you just multiply and then take the high order bits. That's what this is saying. So this is a method more recent, 1997. Whereas this one goes back to 1979. So 79, 97. And it's also universal. Okay, there's a lot of universal hash functions. I'm not going to list them all. I'd rather get to stronger properties than universality. So next one is called k-wise independence. This is harder to obtain, and it implies universality. So we want a family of hash functions such that maybe let's start with just pairwise independence, k equals 2. Then what this is saying is the probability over your choice of hash function that the first key maps to this slot, T1, and the second key maps to some other slot, T2, for any two keys, x1 and xk, should be, if your function was random, each of those happens with probability 1 over m. They're independent, so you get 1 over m to the k, or 1 over m squared for k equals 2. Even in that situation, that's different from saying the probability of two keys being equal is 1 over m. This would imply that. But here, there could still be some codependence between x and y. Here, there essentially can't be, other than this constant factor. Okay, so pairwise independence means every 2 guys are independent. K-wise means every k guys are independent, up to the constant factor. So this is for distinct xi's. Obviously, if two of them are equal, they're very likely to hash to the same slot. So we've got to forbid that. Okay, so an example of such a hash function is here we just took a product. In general, you can take a polynomial of degree k minus 1, evaluate that mod p, and then if you want some modulo that to your table size. So in particular, if k equals 2, we actually have to do some work. This function is not not pairwise independent. It is universal. If you make it ax plus b for random a and b, then this becomes pairwise independent. In general, if you want three y's independent, triple y's independent, you need ax squared plus bx plus c for random a, b's, and c's. So these are arbitrary numbers between 0 and p, I guess. Okay, this is also old, from 1981. Vegman and Carter introduced these two notions in a couple of different papers. This is an old idea. This is, of course, expensive in that we pay order k time to evaluate it. It's also, there's a lot of multiplications, and you have to do everything modulo p. So a lot of people have worked on more efficient ways to do k-wise independence. And there are two main results on this. Both of them achieve n to the epsilon space, which is not great. One of them, the query time depends on k, and it's uniform and reasonably practical. It's experiments. The other one is constant query. For logarithmic independence. So this one is actually later. It's by Thorpe and Zhang. And this is by Siegel. Both 2004. So fairly recent. I guess it takes a fair amount of space. You can actually prove, this paper proves that to get constant query time for logarithmic independence, you need quite a bit of space to store your hash function. Keep in mind, these hash functions only take, this is like k log n bits to store. So we're not, this is words of space. So here we're only spending k words to store this hash function. It's very small. Here you need something depending on n, which is kind of annoying, especially if you want to be dynamic. But statically, you can get constant query logarithmic wise independence, but you have to pay a lot in space. And then, there's more practical methods. This is especially practical for k equals 5, which is a case that we'll see is of interest. Cool. So this much space is necessary if you want. We'll see log-wise independence is the most we'll ever require in this class. And as far as I know, in hashing in general. So you don't need to worry about more than log-wise independence. All right. One more hashing scheme. It's called simple tabulation hashing. This is a simple idea. It goes also back to 81, but it's just been analyzed last year. So there's a lot of results to report on it. The idea is just take your integer, split it up into some base, so that there's exactly C digits, or we'll call them characters. C is going to be a constant. Then build a totally random hash table. This is the thing that we couldn't afford. But we're just going to do it on each character. So there's going to be C of these hash tables. And each of them is going to have size u to the 1 over c. So essentially we're getting u to the epsilon space, which is similar to these space bounds. So again, not great, but it's a really simple hash function. Hash function is just going to be you take your first table, apply it to the first character, XOR that with the second table applied to the second character, and so on through all the characters. So a nice thing about this is it's super simple. You can imagine this being done probably in one instruction on a fancy CPU. If you convince people this is a cool enough instruction to have. It's very simple to implement circuit-wise. But in our model, where you have to do all these operations separately, you're going to take order C time to compute. And the one thing that's known about it is that it's 3 independent. 3-wise independent. So it does kind of fit in this model. But 3-wise independence is not very impressive. A lot of the results we'll see require log n independence. But the cool thing is, roughly speaking, simple tabulation hashing is almost as good as log n-wise independence in all the hashing schemes that we care about. And so we'll get there, exactly what that means. So that was my overview of some hash functions, these two guys. Next we're going to look at basic chaining. Perfect hashing. How many people have seen perfect hashing, just to get a sense? Okay, more than half, maybe 2/3. All right, I should do this really fast. Okay, chaining. This is the first kind of hashing you usually see. You have your hash function, which is mapping keys into slots. If you have 2 keys that go to the same slot, you store them as a linked list. Okay, if you don't have anything in the slot, it's blank. So this is very easy. If you look at a particular slot T and call the length of the chain that you get there CT, you can look at the expected length of that chain. In general, it's just going to be some probability that the keys map to that slot, and then you sum over all keys. This is just writing this as a sum of indicator random variables, and then each expectation, linearity of expectation of each of the indicator variables is a probability. So that is the expected number. And fine. So here we just need to compute the probability that each guy goes to each slot. As long as your hash function is uniform, meaning that each of these guys is sort of equally likely to be hashed to. Well, actually, we're looking at particular slots, so we're essentially using universality here. Probability, once we fix one slot that we care about, so let T be some h of y that we care about, then this is universality. By universality, we know this is 1 over m. And so this is whatever n over m, usually called the load factor. And what we care about is this is constant for m equal theta n. And so use table doubling to keep m theta n. Boom, you've got expected chain length constant. But in this world, in the theory world, expected is a very weak bound. What we want are high probability bounds. So let me tell you a little bit about high probability bounds. This you may not have seen as much. So let's start with, if your hash function is totally random, then your chain lengths will be order log n over log n with high probability. They are not constant. In fact, you expect the maximum chain to be at least log n over log n. I won't prove that here. Instead, I'll prove the upper bound. So claim is that while in expectation each of them is constant, the variance is essentially high. You can get, well, actually, yeah, fine. Actually, let's talk about variance a little bit. Sorry, getting distracted. So you might say, oh, okay, expectation is nice. Let's look at variance. Turns out variance is constant for these chains. There are various definitions of variance, but in particular, the formula I want to use is this one. Writes it as some expectations. Now this, the expected chain length we know is constant, so you square it, it's still constant. So that's sort of irrelevant. The interesting part is what is the expected squared chain lengths? Now this is going to depend exactly on your hash function. Let's analyze it for totally random. In general, we just need a kind of symmetry here. You can write, yeah, sorry, where am I? Here. I will look at the expected squared chain lengths. And instead, what I'd like to do is just sum over all of them. This is going to be easier to analyze. So this is the expected squared chain lengths. If I sum over all chains and then divide, take the average, then I'll probably get the expected chain length of any individual. As long as your hash function is symmetric, all the keys are sort of equally likely, this will be true. And then you could just basically apply a random permutation to your keys to make this true if it isn't already. So now this thing is just the number of pairs of keys that collide. So you can forget about slots. This is just the sum over all pairs of keys ij of the probability that xi hashes to the same spot as xj. And that's something we know by universality. This is 1 over m, big O. The number of pairs is m squared. So we get m squared times 1 over m times 1 over m. This is constant. Okay. So variance is actually small. That's not a good indicator of how big our chains can get. Because still, with high probability, one of the chains will be log n over log n. It's just typical one won't be. Let's prove the upper bound. This uses Chernoff bounds. So this is a tail bound, essentially. I haven't probably defined with high probability. It's probably good to remember. Review this. This means probability at least 1 minus 1 over n to the c, where I get to choose any constant c. So that's high probability means polynomially small failure probability. This is good because if you do this polynomially many times, this property remains true. You just up your constant by however many times you're going to use it. So we prove these kinds of bounds using Chernoff, which looks something like this. E to the c minus 1 mu over c mu c mu. So mu here is the mean. The mean we've already computed is constant. The expectation of the CT variable is constant. So we want it to be not much larger than that. So we say the probability that it's some factor larger, c doesn't have to be constant here, sorry, but maybe not great terminology. So the probability that CT is at least some c times the mean is going to be at most this exponential, which is a bit annoying or a bit ugly. But in particular, if we plug in c equals log n over log n, use that as our factor, which is what we're concerned about here, then we get that this probability is essentially dominated by the bottom term here. And this becomes log n over log log n to the power log n over log log n. So essentially get 1 over that. And if you take this bottom part and put it into the exponent, you get essentially log log n. So this is something like 1 over 2 to the log n over log log n times log log n. And the log log n's cancel, and so this is basically 1 over n. And if you put a constant in here, you can get a constant in the exponent here. So you can get failure probability 1 over n to the c. So get this with high probability bound as long as you go up to a chain length of log n over log log n. It's not true otherwise. So this is kind of depressing. It's one reason we will turn to perfect hashing. Some of the chains are long. But there is a sense in which this is not so bad. So let me go to that. Kind of want all these. What's that? Since when is log n long? Well, yeah. Right. So I mean, in some sense, the name of the game here is we want to beat binary search trees, right? I didn't even mention what problem we're solving. We're solving the dictionary problem, which is store a bunch of keys, insert, delete, and search is now just exact search. I want to know, is this key in there? If so, find some data associated with it, which is something binary search trees could do in log n time. And we've seen various fancy ways to try to make that better. But in the worst case, you need log n time to do binary search trees. We want to get to constant as much as possible. So we want the hash function to be evaluatable in constant time. We want the queries to be done in constant time. If you have a long chain, you've got to search the whole chain. And I don't want to spend log n over log log n, because I said so. Admittedly, log n over log log n is not that big. And furthermore, the following holds. This is a sense in which it's not really log n over log log n. If we change the model briefly and say, well, suppose I have a cache of the last log n items that I searched for in the hash table. Then if you're totally random, which is something we assumed here, in order to apply the Chernoff bound, we needed that everything was completely random. Then you get a constant amortized bound per operation. So this is kind of funny. In fact, all it's saying, this is easy to prove. And it's not yet in any paper. It's on Mihai Petrashku's blog from 2011. You take... All right, we're here. We're looking at different chains. So you access some chain, then you access another chain, then you access another chain. If you're unlucky, you'll hit the big chain, which costs log n over log log n to touch, which is expensive. But you could then put all those guys into cache, and if you happen to keep probing there, it should be faster. In general, you do a bunch of searches. Okay, first I search for x1, then I search for x2, x3, so on. Cluster those into groups of theta log n. Okay, let's look at the first log n searches, then the next log n searches, and analyze those separately. We're going to amortize over that period of log n. So if we look at theta log n, actually, this is written in a funny way. Got the theta, just log n. So I'm going to look at a batch of log n operations, and I claim that the number of keys that collide with them is theta log n with high probability. Okay, if this is true, then I just charge, then it's constant each. If I can do log n operations by visiting order log n total chain items with high probability, then I just charge 1 each. And so amortized over this little log n window of sort of smoothing the cost, with high probability now, not just expectation, I get constant amortized per operation. So I should have said with high probability. Why is this true? It's essentially the same argument. Here, this is normally called a balls and bin argument. So you're throwing balls, which are your keys, randomly into your bins, which are your slots. And the expectation is constant. Probability any one of them, any one of them could go up to log n over log n, high probability. Over here, we're looking at log n different slots and taking the sum of balls that fall into each of the slots. And in expectation, that's log n, because it's constant each. And expectation is linear, if you're taking the sum over these log n bins. So the expectation is log n. So you apply Chernoff again, except now the mean is log n. And then it suffices to put c equals 2. We can run through this. So here we get the mean is theta log n. We expect there to be log n items that fall into these log n bins. And so you just plug in c equals 2 to the Chernoff bound, and you get, let's see, e to the log n, which is kind of weird, over 2 log n to the 2 log n. So this thing is like roughly this is like n to the log n, 2 even. So this is big, way bigger than this. So this essentially disappears. And in particular, this is bigger than n to the c, 1 over n to the c for any c. So log n is bigger than any constant. So you're done. So that's just saying the probability that you're more than twice the mean is very, very small. So with high probability, it's only log n items that fall in these log n bins. So you just amortize, boom, constant. This is kind of a weird notion. I've never actually seen amortize with high probability ever in a paper. This is the first time it seems like a useful concept. So if you think log n over log n is bad, this is a sense in which it's okay. Don't worry about it. All right. But if you did worry about it, next thing you do is perfect hashing. So perfect hashing is really just an embellishment on, this is also called FKS hashing from the authors, Fredman, Komlosh, and Semeredi. This is from 1984, so old idea. You just take chaining, but instead of storing your chains in a linked list, store them in a hash table. Simple idea. There's one clever trick. You store it in a big hash table. Hash table of size, call it theta ct squared. Now this looks like a problem because that's going to be quadratic space in the worst case if everybody hashes to the same chain. But we know the chains are pretty small with high probability. So turns out this is okay. The space is sum of ct squared. Okay, so, and that's something we actually computed already, except I erased it. How convenient of me. It was right here. I can still barely read it. When we computed the variance, we can do it again. It's not really that hard. This is the number of pairs of keys that collide. And so this is, there's n squared pairs, and each of them has a probability 1 over m of colliding if you have a universal hash function. So this is n squared over m, which if m is within a constant factor of n, is linear. So linear space in expectation. Sorry. Expected amount of space is linear. I won't try to do it with high probability bound here. What else can I say? You have to play a similar trick when you're actually building these hash tables. All right, so why do we use n squared? Because of the birthday paradox, right? So if you have a hash table of size n squared, essentially, or ct squared, the probability, with high probability or constant probability, you don't get any collisions. Why? Because then the expected number of collisions in CT, well, there's CT pairs, or CT squared pairs. Each of them, if you're using universal hashing, has probability of 1 over CT squared of happening, because that's the table size, 1 over m. So this is constant. And if we set the constants right, I get to set this theta to be whatever I want. I get this to be less than a half. And if the expected number of collisions is less than a half, then the probability that the number of collisions is 0 is at least a half. This is Markov's inequality in particular. The probability number of collisions is at least 1, is at most the expectation over 1, so which is a half. So you try to build this table. If you have 0 collisions, you're happy, you go on to the next one. If you don't have 0 collisions, just try again. So in an expected constant number of trials, you're flipping a coin each time. Eventually you'll get heads. Then you can build this table, and then you have 0 collisions. So we always want them to be collision-free. So in expected linear time, you can build this table, and it will have expected linear space. In fact, if it doesn't have linear space, you can just try the whole thing over again. So in expected linear time, you'll build a guaranteed linear space structure. Nice thing about perfect hashing is you're doing 2 hash dereferences, and that's it. So the query is constant deterministic. Queries are now deterministic. Only updates are randomized. I didn't talk about updates. I talked about building. The construction here is randomized. Queries are constant deterministic. Now, you can make this dynamic in pretty much the obvious way. You say, okay, I want to insert, so I compute the first, I compute which of the, this is essentially 2-level hashing, right? So first you figure out where it fits in the big hash table, then you find the corresponding chain, which is now a hash table, and you insert into that hash table. So that's the obvious thing. The trouble is you might get a collision in that hash table. If you get a collision, you rebuild that hash table. Probability of the collision happening is essentially small. It's going to remain small because of this argument, because we know the expected number of collisions remains small, unless that chain gets really big. So if the chain grows by a factor of 2, then you rebuild. I mean, generally we have to rebuild the table. But if your table grows by, if your chain length grows by a factor of 2, then you rebuild your table to have factor 4 size larger because it's CT squared. And in general, you maintain that the table is sized for a chain of roughly the correct chain length within a constant factor, and you do doubling and halving in the usual way as like B-tree, or I guess as table doubling, really. And it will be constant amortized expected per operation. And there's a fancy way to make this constant with high probability per insert and delete, which I have not read, but it's by Dietz-Filbinger and Meyer-Aufderheide, 1990. So easy to make this expected amortized. With more effort, you can make it with high probability per operation. That is trickier. Cool. I actually skipped one thing with chaining, which I wanted to talk about. So this analysis was fine. It just used universality. But this cache analysis, I said totally random. This analysis, I said totally random. What about real hash functions? We can't use totally random. What about universal, ky is independent, simple tabulation hashing, just for chaining. Okay, and similar things hold for perfect hashing, I think. I'm not sure if they're all known. Perfect hashing, in expectation, everything's fine, just with universal. So we've already done that with universal. What about chaining? How big can the chains get? Said log n over log log with high probability, but our analysis used a Chernoff bound that's only true for Bernoulli trials. That's only true for totally random hash functions. Turns out, same is true if you have a log n over log log n wise independent hash function. So this is kind of annoying. If you want this to be true, you need a lot of independence. And it's hard to get log n independence. I mean, there is a way to get constant, but it needed a lot of space. That was this one, which is not so thrilling. It's also kind of complicated. So if you don't mind the space, but you just want it to be simpler, you can use simple tabulation hashing. Both of these, the same chain analysis turns out to work. So this is fairly old. This is from 1995. This is from last year. So if you just use this simple tabulation hashing, still has a lot of space, u to the epsilon, but very simple to implement, then still the chain lengths are as you expect them to be. And I believe that carries over to this caching argument, but I haven't checked it. All right. Great. I think we're now happy. We've talked about real hash functions for chaining and perfect hashing. Next thing I'm going to talk about is linear probing. I mean, in some sense, we have good theoretical answers now, right? We can do constant, expected, amortized, even with constant deterministic queries. But we're greedy, or people like to implement all sorts of different hashing schemes. Perfect hashing is pretty rare in practice. Why? I guess because you have to hash twice instead of once, and that's just more expensive. So what about the simpler hashing schemes? Simple tabulation hashing is nice and simple, but what about linear probing? That's really simple. Linear probing is either the first or the second hashing scheme you've learned. You store things in a table. When you want, you hash. The hash function tells you where to go. If that's full, you just go to the next spot. If that's full, you go to the next spot until you find an empty slot, and then you put x there. Okay, so if there's some y and z here, that's where you end up putting it. Everyone knows linear probing is bad, because the rich get richer. It's like the parking lot problem. If you get big intervals, then they're more likely, big runs of elements, they're more likely to get hit. So they're going to grow even faster and get worse. So you should never use linear probing. That's what you have everyone learned that? It's all false, however. Linear probing is actually really good. And first indication is it's really good in practice. There's this small experiment by Mihai Petrescu, who was an undergrad and PhD student here. He's working at AT&T now, and he was doing some experiments, and he found that in practice on a network router, linear probing costs 10% more time than a memory access. So basically free. Why? You just set m to be 2 times n, or 1 plus epsilon times n. Whatever. It actually works really well. I'd like to convince you that it works really well. Now, first let me tell you some things. The idea that it goes really well is actually that it works really well is old. For a totally random hash function, you require constant time per operation. And Knuth actually showed this first in 1962 in a technical report. The answer ends up being 1 over epsilon squared. Now you might say 1 over epsilon squared, oh, that's really bad. And there are other schemes that achieve 1 over epsilon, which is better. But what's a little bit of space, right? I mean, just set epsilon to 1, you're done. So I think linear probing was bad when we really were tight on space. But when you can afford a factor of 2, linear probing is great. That's the bottom line. Now, this is totally random, not so useful. What about all these other hash functions, like universal? Turns out, with the universal hash function, linear probing is really, really bad, and that's why it gets a bad rap. But some good news. OK, first result was log n-wise independence. This is extremely strong, but it also implies constant expected per operation. Not very exciting. The big breakthrough was in 2007 that 5-wise independence is enough. And this is why this paper, Thorpe, was focusing in particular on the case of k equals 5. Actually, they were doing k equals 4, but they solved 5 at the same time. And so you can get, this was a highly optimized, practical, all that good stuff. Get 5-wise independence, admittedly with some space, but it's pretty cool. And so this is enough to get constant expected. I shouldn't write order 1 because I'm not writing the dependence on epsilon here. I don't know exactly what it is, but it's some constant depending on epsilon. And then this turns out to be tight. There are 4-wise independent hash functions, including the ones, I think the polynomial ones that we did, these guys, that are really bad. You can get, really bad. They're as bad as binary search trees. You can get constant expected. So you really need 5-wise independence. It's kind of weird, but it's true. And the other fun fact is that simple tabulation hashing also achieves constant, and here it's known that it's also 1 over epsilon squared. So it's just as good as totally random simple tabulation hashing, which is nice because again, this is simple, takes a bit of space, but both of these have that property, and so these are good ways to use linear probing in particular. So you really need a good hash function for linear probing to work out. If you use a universal hash function like a times x mod p mod m, it will fail. But if you use a good hash function, which we're now getting to the point, this is super simple to implement, should work fine. I think it'd be a neat project to take Python or something that has hash tables deep inside it, replace, I think they use quadratic probing and universal hash functions. If you instead use linear probing and simple tabulation hashing, might do the same, might do better, I don't know. It's interesting. It would be a project to try out. Cool. Well, I just quoted results. What I'd like to do is prove something like this to you. Totally random hash functions imply some constant expected. I won't try to work out the dependence on epsilon, because it's actually a pretty clean proof. Looks nice. Very data structures-y. I'm not going to cover Knuth's proof. I'm essentially covering this proof. The 5-wise, in this paper, 5-wise independence implies constant expected. They reprove the totally random case and strengthen it, analyze the independence they need. But let's just do totally random implies constant expected for linear probing. Okay, we obviously know how to do constant expected already with other fancy techniques, but linear probing seems really bad, yet I claim not so much. And we're going to assume m is at least 3 times n. That will just make the analysis cleaner, but it does hold for 1 plus epsilon. Okay, so here's the idea. We're going to take our array, our hash table, It's an array. And build a binary tree on it, because that's what we like to do. We do this in every lecture, pretty much. So this is kind of like ordered file maintenance, I guess. This is just a conceptual tree. I mean, you're not even defining an algorithm based on this, because the algorithm is linear probing. You go into somewhere, you hop, 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 hop until you find a blank space, you put your item there. Okay, but each of these nodes defines an interval in the array, as we know. So I'm going to call a node dangerous if essentially if its density is at least 2/3. Now the but not in the literal sense, because there's a little bit of a subtlety here. There's the location where a key wants to live, which is h of that key, and there's the location that it ended up living. I care more about the first one, because that's what I understand. The h of x, that's going to be nice. It's totally random. So h of x is random, independent of everything else. Great. Where x ends up being, that depends on other keys, and it depends on this linear thing, which I'm trying to understand. So I just want to talk about the number of keys that hash via h to the interval, if that is at least 2/3 times the length of the interval. This is the number of slots that are actually there. Okay, we expect the number of keys that hash via h to the interval to be 1/3. So the expectation would be 1/3 the length of the interval. If it happens to be 2/3, it could happen because of high probability, whatever. That's a dangerous node. That's the definition. Those ones we worry will be very expensive. And we worry that we're going to get super clustering and then get these giant runs and so on. So, okay, one thing I wanted to compute was what's the probability of this happening. Probability of a node being dangerous. Well, we can again use turn-off bounds here because we're in the totally random situation. So this is the probability that the number of things that went there was bigger than twice the expectation. The expectation is 1/3, 2/3 is twice of 1/3. So this is the probability that you're at least twice the mean, which by turn-off is small. It comes out to e to the mu over 2 to the 2 mu. Great. So this is e over 4 to the mu. You can check e. It's 2.71828. So this is less than 1. Kind of roughly a half-ish. So this is good. This is something like 1 over 2 to the mu. What's mu? Should know that. Mu is 1/3, 2 to the h for a height h node. Okay, it depends how high you are. If you're at a leaf, h is 0. So you expect 1/3 of an element there. As you go up, you expect more elements to hash there, of course. Okay, so this gives us some measure in terms of this h of what's going on. But it's actually doubly exponential in h. So this is a very small probability. You go up a few levels. Like after log n levels, it's a polynomially small probability of happening. Because then 2 to the log n is log n, and then e over 4 to the log n is about n. But this at small levels, this may happen near the leaves. All right, so now I want to look at a run in the table. These are the things I have trouble thinking about because runs tend to get bigger and we worry about them. This is now, as items are actually stored at the table, when do I have a bunch of consecutive items in there? okay, that happen to end up in consecutive slots. So I'm worried about how long that run is. So let's look at its logarithm. Okay, and round to the nearest power of 2. So let's say it has length about 2 to the L. Sorry, plus 1. Okay, between 2 to the L and 2 to the L plus 1. Okay, so look at that. And it's spanned by some number of nodes of height h equals L minus 3. Okay, so there's some interval that happens to be a run, meaning all of these slots are occupied. And that's 2 to the 2, I guess. And so I'd go to level -1. A little hard to do in a small picture. But we're worried about when this is really big, more than some constant. Okay, so let's suppose I was looking at this level. Then this interval is spanned in particular by these 2 nodes. Now, it's a little sloppy because this node contains some non-interval, non-run stuff, and so does this one. At the next level down, it would be this one, and this one, which is a little more precise, but it's never going to be quite perfect. But just take all the nodes you need to completely cover the run. Then this will be at least 8 nodes, because, I mean, the length is 2 to the L. We went 3 levels down. 2 to the 3 is 8. So if it's perfectly aligned, it will be exactly 8 nodes. In the worst case, it could be as much as 17, because potentially we're 2 to the L plus 1, which means we have 16 nodes if we're perfectly aligned. But then if you shift it over, it might be 1 more because of the slop. Okay, but some constant number of nodes. It's important that it's at least 8. That's what we need. Actually, we just need that it's at least 5, but 8 is the nearest power of 2, rounding up. Cool. So there they are. Now, I want to look at the first 4 nodes of these 8 to 12 nodes. So first meaning leftmost, earliest in the run. So if you think about them, so there's some 4 nodes. Each of them spans some, I should draw these properly. What we know is that these guys are entirely filled with items. The run occupies here. It's got to be at least 1 item into here, but the rest of this could be empty. The interval keeps going to the right, so we know that all of these are completely filled with items somehow. So let's start with how many there are, I guess. They span more than 3 times 2 to the h slots of the run. So somehow, 3 times 2 to the h, 3, because there's 3 of them that are completely filled, otherwise it would be 4. Somehow 3 times 2 to the h items ended up here. Now, how did they end up here? Notice there's a blank space right here. This was by definition, this is the beginning of a run, meaning the previous slot is empty, which means all of the keys that wanted to live from here to the left got to. So if we're just thinking about the keys that ended up in this interval, they had to initially hash to somewhere in here. H put them somewhere in this interval, and then they may have moved to the right, but they'd never moved to the left by linear hashing if you're not completely full. So because there was a blank spot here, none of these keys could have fallen over to here. We have no deletions. Okay? So you're doing insertions. If they may have spread it out, and they may have gone farther to the right, or they may have filled in gaps, whatever. But H put them in this interval. Okay. Now, I claim that in fact, at least one of these nodes must be dangerous. Now, dangerous is tricky because dangerous is talking about where H puts nodes. But we just said we've got to be at least 3 times 2 to the H keys where H put them within these 4 nodes. Otherwise, they wouldn't have filled in here. Now, if none of those nodes were dangerous, then we'll get a contradiction. Because none of them were dangerous, this means at most 4 times 2/3 times 2 to the h keys hash via h to them. Why? Because there's 4 of the nodes. Each of them, if it's not dangerous, it has at most 2/3 of its size. Keys hashing there. 4 times 2/3 is 8/3, which is less than 9/3, which is 3. Okay, so this would be a contradiction because we just argued that at least 3 times 2 to the h nodes have to hash via h to somewhere in these nodes. They might have hashed, well, they might hash here and then fallen over to here. So there's this kind of things can move to the right. We've got to worry about it. But just look 3 levels up, and it's OK. So one of these nodes, not necessarily all of them, are dangerous. And we can use that to finish our analysis. This is good news because it says that if we have a run, which is something that's hard to think about because nodes are moving around to form a run, so keys are moving around to form a run, we can charge it to a dangerous node, which is easy to think about because that's just talking about where keys hash via h, and h is totally random. There's a loss of a factor of 17 potentially, but it's a constant factor, no big deal. If we look at the probability that the length of a run, say containing some key x, has length between 2 to the L and 2 to the L plus 1, this is going to be at most 17 times the probability of a node at height L minus 3 is dangerous. Because we know one of them is, and so just to be sloppy, it's at most the sum of the probabilities that any of them is, then potentially there's a run of that length, and so union bound, it's at most 17 times probability of this happening. Now, all the nodes look the same because we have a totally random hash function. So we just say any node at height L minus 3. And we already computed that probability. That was this. Probability of being dangerous was e over 4 to the 1/3 2 to the h. So this is going to be 17, or at most 17 times e over 4 to the 2 to the L minus 3 power. Okay, again, doubly exponential in L. So if we want to compute the expected run length, we can just expand out the definition. Well, let's round it to powers of 2. It could be the run length is about 2 to the L within a constant factor of 2 to the L. And so it's going to be that times the probability, well, this probability. But this thing is basically 1 over 2 to the 2 to the L. And so the whole thing is constant. This is L. I mean, L could go to infinity. I don't really care. Because this is, I mean, this gets dwarfed by the double exponential. So this is super geometric. So very low probability of getting long runs. As we said, after log n size, or after, yeah, it's very unlikely to get a run longer than log m. We prove that in particular. But in particular, you compute the expected run length. It's constant. Okay, now this, of course, assumed totally random. It's harder to prove. Where were we? Somewhere. Linear probing. It's harder to prove 5-wise independence is enough, but it's true. And it's much harder to prove simple tabulation hashing works, but it's true. And so we can use them. But this gives you some intuition for why it's really not that bad. And similar proof techniques are used for the 5-wise independence. Other fun facts, you can do a similar caching trick that we did before. Again, the worst run is going to be, I don't know, log or log over log log. I don't have it written here. But if you cache the last, it's not quite enough to do the last log n, but if you cache the last log to the 1 plus epsilon n queries, so a little bit more, then you can generalize this argument. And so at least for totally random hash functions, you get constant amortized with high probability. This weird thing that I've never seen before. But it's comforting because expected bounds are not so great, but you get it with high probability bound as long as you're willing to average over log to the 1 plus epsilon different queries, as long as you can remember them. And the proof is basically the same, except now instead of looking at the length of a run containing x, you're looking at the length of the run containing one of these log to the 1 plus epsilon n nodes. That's your batch. And you do the same thing, but now do it with high probability analysis. But again, because the expectation is now bigger than log, you expect there to be a lot of fairly long runs here, but that's okay because on average it's good. You expect to pay log to the 1 plus epsilon for log to the 1 plus epsilon queries. And so then you divide and amortize and you're done. So a little bit more details in the notes about that if you want to read. I want to do one more topic, unless there are questions about linear probing. So, yeah.
So could you motivate why the pick value of mu is the mean for whatever quantity?
So mu is defined to be the mean of whatever quantity we're analyzing. And the Chernoff bound says probability that you're at least something times the mean is the formula we wrote last time. Now here, we're measuring, I didn't write what the left-hand side was, but here we're measuring what's the probability that the number of keys that hash via h to the interval is at least 2/3 the length of the interval. Now, if m is at least, or let's say m equals 3n, then the expected number of keys that hash via h to the interval is 1/3 times the length of the interval. Because we have a totally random thing, and we have a density of 1/3 overall. So you expect there to be 1/3, and so dangerous is when you're more than twice that. And so it's twice mu. Mu is, in this case, 1/3 the length of the interval, and that's why I wrote that.
Okay, so this comes from the m is greater than or equal to 3n.
Yeah, it comes from m equals 3n and totally random.
So some of these equalities should be like...
Yeah, okay, let's make this equal. Make this more formal. It's an assumption anyway, so to simplify the proof. Good. Change that in the notes too. Cool. So then the expectation is exactly 1/3 instead of at most 1/3, so it's all a little cleaner. Of course, this all works when m is at least 1 plus epsilon times n, but then you get a dependence on epsilon. Other questions? So bottom line is linear probing is actually good. Quadratic probing, double hashing, all those fancy things are also good, but they're really tuned for the case when your table's almost full. They get a better dependence on epsilon, which is how close to the bound you are. And so if you're constant factor away from space-bound, linear probing is just fine. as long as you have enough independence, admittedly. Double hashing, I believe, gets around that. It does not need so much independence. Okay, but instead of going to double hashing, I'm going to go to something kind of related to double hashing, which is cuckoo hashing. Cuckoo hashing is a weird idea. It's kind of a more extreme form of perfect hashing. It says, look, I want to... perfect hashing did 2 hash queries. So I did 1 hash evaluation, another hash evaluation. Follow it, which is OK. But again, I want my queries to only do 2 things, 2 probes. So it's going to take that concept of just 2. And actually use two hash tables. So we've got B over here. And we've got A over here. And we're going to have, if you have a key X, you hash it to a particular spot in A via G, and you hash it to a particular spot in B via H. So I have 2 hash tables, 2 hash functions. To do a query, you look at A of G of X, and you look at B of H of X. Oh, sorry, I forgot to mention, the other great thing about linear probing is its cache performance is so great. This is why it runs so fast in practice, why it's only 10% slower than a memory access. Because once you access a single slot, you get B slots in a cache with block size B. So most of the time, because your runs are very short, you will find your answer immediately. So that's why we kind of prefer linear probing in practice over all the other schemes I'm going to talk about. Well, cuckoo hashing is all right, because it's only going to look at 2 places, and that's it. It doesn't go anywhere else. So kind of like, I guess with perfect hashing, the thing is, you have more than 2 hash functions. You have the first hash function, which sends you to the first table. Then you look up a second hash function. Using that hash function, you rehash your value x. Downside of that is you can't compute those 2 hash functions in parallel. So if you're like 2 cores, you could compute these 2 in parallel, look them both up simultaneously. So in that sense, you save a factor of 2 with some parallelism. Now, the weird thing is the way we do an insertion. You try to put it in the A slot, I guess, or the B slot. If either of them is empty, you're golden. If neither of them are empty, you've got to kick out whoever's there. So let's say if you kicked out Y from its A slot, so we ended up putting X in this one, and so we end up kicking Y from wherever it belonged, then you move it to B of H of Y. There's only one other place that that item can go, so you put it there instead. Okay. In general, think about a key. It has 2 places it can go. There's some slot in A, some slot in B. You can think of this as an edge in a bipartite graph. So you make vertices for the A slots, vertices for the B slots. Each edge is an item, a key. Key can only live in 1 spot in A, 1 spot in B for this query to work. So what's happening is if both of these are full, you take whoever is currently here and put them over in their corresponding slot over in B. Now that one might be full, which means you've got to kick that guy to wherever he belongs in A, and so on. If eventually you find an empty slot, great, you're done. This chain reaction of of cuckoo steps, I guess, where the bird's going from in and out, or from A to B, vice versa. If it terminates, you're happy. If it doesn't terminate, you're in trouble because you might get a cycle or a few kind of failure situations. In that case, you're screwed. There is no cuckoo hash table that works for your set of keys. In that case, you pick another hash function, rebuild from scratch. So it's kind of a weird hashing scheme because it can fail catastrophically. Fortunately, it doesn't happen too often. So it still rubs me a funny way. I don't know what to say about it, but okay. So you lose a factor of 2 in space. It's 2 deterministic probes for a query. That's good news. It's all right. Now we get to what about updates? So if it's fully random or log ny is independent, then you get constant expected update, which is what we want, even with the rebuilding cost. So you'll have to rebuild about every n squared insertions you do. The way they say this is there's a 1 over n build failure probability. There's a 1 over n chance that your key set will be completely unsustainable. If you want to put all n keys into this table, there's a 1 over n chance that it will be impossible, and then you have to start over. So amortized per insertion, that's about 1 over n squared. Insertions you can do before the whole thing falls apart, and you have to rebuild. So it's definitely going to be amortized. This should be amortized expected, I guess. However you want to think about it. But it's another way to do constant amortized expected. Cool. The other thing that's known is that 6-wise independence is not enough. This was actually a project in this class, I believe the first time it was offered in 2003. 6-wise independence is not sufficient to get constant expected bound. You can have it will actually fail with high probability if you only have 6-wise independence. What's not known is, do you need constant independence or log n independence? With log n, very low failure probability. With 6-wise, high probability you fail. Like you fail with probability 1 minus 1 over n. Not so good. That's some good news is simple tabulation hashing. Means you will fail to build with probability not 1 over n, but 1 over n to the 1/3 power. So this is a little, and this is theta, this is tight. It's almost as good as this. We really only need constant here. This is to build the entire table. So in this case, you can insert like n to the 4/3 items before your table self-destructs. So simple tabulation hashing is, again, pretty good. That's I think the hardest result in this paper from last year. Yeah. So I do have a proof of this one. Something like that, or part of a proof. Let me give you a rough idea how this works. So if you have a fully random hash function, the main concern is that what if this path is really long? I claim that if an insert follows a path of length k, or the probability of this happening is actually at most 1 over 2 to the k. It's very small, exponentially small in k. And to give you, I just want to sketch how this works because it's a cool argument that's actually in this simple tabulation paper. So the idea is the following. You have some really long path. What I'm going to give you is a way to encode the hash values or the hash functions. Okay, how many? There's hash functions G and H. Each of them has n values. Each of those values is log m bits. Right. So if I just wrote them down the obvious way, it's 2 n log m bits to write down those hash functions. Now we're assuming these are totally random hash functions, which means you need this many bits. But I claim that if you follow a path of length k, I can find a new encoding scheme, a way to write down G and H that is basically minus k. This many bits minus k. I get to save k bits. Now, it turns out that can happen, but it happens only with probability 1 over 2 to the k. This is an information theoretic argument. You might get lucky, and the 8 G's and H's you're trying to encode can be done with a few fewer bits, k fewer bits, but that will only happen with probability 1 over 2 to the k if G and H are totally random. So how do you do it, basically? I want to encode the things on the path slightly cheaper. I'm going to save 1 bit per node on the path. So what do I need to do? Well, the idea is, OK, I will start by writing down this hash value. OK, this takes log m bits to write down that hash value. Then I'll write down this hash value. That takes log m bits, log m bits. Generally, is going to be roughly k log n to write down all of the node hash values. Then I need to say that it's actually x, this particular key that corresponds to this edge. So I've got to write that down. That's going to take log n bits to say that x is the guy for the first edge, then y is the key that corresponds to the second edge of the path, then z, then w. But nicely, things are ordered here. So it only takes me log n, k log n, to write down all these guys. So I get k times log m plus log n. Now, if m is 2 times n, this is k times 2, times 2 log m minus 1. So I get 1 bit of savings per k, per thing in the path, essentially because it's easier for me to write down these labels to say, oh, it's the key x that's going here. Instead of having to write down slot names all the time, which cost log m bits, writing down key names only takes log n bits, which is a savings of 1 bit per thing on the path. And so, well, that's a quick sketch of how this proof goes. But it's kind of neat. It's an information theoretic argument why the paths can't get long. You don't have to worry about cycles and things that look like this. It's kind of messy, but same kind of argument generalizes. So that was your quick overview of lots of hashing stuff.